Okay, so now we have seen position and velocity vectors in polar frame. It is time to define acceleration. We have velocity, so we can take acceleration as time derivative of velocity. You can do all the cool stuff, r double dot ur plus r dot ur dot plus so on. Let me write it down. You have r dot theta dot u theta plus r theta double dot u theta plus r theta dot u theta dot. Okay, a few weird terms like this one, like that one. We can follow the same procedure as we had before. Ooh, down the road, some math, we can get to this equation. Acceleration equals r double dot minus r theta dot squared in radial direction. Let me clean up here. Okay. Plus some r theta double dot plus 2 r dot theta dot in the transverse direction. And that is acceleration. A little big. We have 4 terms. 2 of them add up to make the radial component of acceleration, and the other 2 add up to make the transverse component of acceleration. The proof or derivation is in the textbook or any reference you can find. Feel free to look at those, but here I want to walk you through what they actually mean. So as before, when I was showing the velocity, we have 4 terms. The first one is r double dot. Essentially same as before. If you assume your motion is just along a straight line going back and forth, the rate of, or the second rate of change of your distance is some acceleration in that direction. So that is the first one. R double dot is only due to acceleration of the distance from the origin. The second term is r theta dot. Theta dot squared. And let's see what this is. Let me bring your attention back to here. R theta dot. This was the transverse component of acceleration. So you can write r theta dot equal, let me do this. R theta dot was v theta, or theta dot is v theta over r. Now substitute this in that, you have r v theta over r squared, or v theta squared over r. And this form looks familiar. It is the same thing, almost the same thing as centripetal acceleration, or the acceleration in the normal direction that we had in the normal tangential frame. So if you assume you're going around a circle in the most simple case, and you're going with constant velocity or constant speed along that path, you will have some, change color, you will have some acceleration toward the center. In the normal tangential frame, we called it v squared over radius of curvature. It's the same thing but with a different set of variables, include theta, but it is a centripetal acceleration pointing toward the center of the curve, or the origin. And because we have assumed our radial component to be outward, the term is actually negative, so it is in the opposite direction of the positive radial component. Oh, why have I written here ut? It should be ur. So these two are the radial component. Both of these are along the line that points from the origin to the location of the particle. R double dot, assuming the positive direction being outward, is positive. The centripetal acceleration, r theta dot squared, is toward the center, so opposite of radial axis. What about the transverse components? We have r theta double dot. Again, r theta double dot is easier to conceptualize if you have a pure circle. That is not a good circle, but it is what it is, and it's not great. So if you are moving along a circle and your angular velocity is increasing, so you're going faster and faster, rotating faster, increasing the angular speed, essentially means your speed should increase, and in that case you have an acceleration in the direction of increasing velocity. So your acceleration would be in the transverse direction. So that is one component. The last one is this 2r dot theta dot. Probably this is the most peculiar one. Actually, it is one of the most famous one. At least it has a name. It is called Coriolis acceleration. And it comes out of math, out of the derivation. But there's actually a very reasonable explanation why this shows up. Consider a condition that you are moving away from the center with constant rate. So your r dot is constant. And also at the same time rotating about the center with constant angular speed. So you have this r and theta, both of them increasing at constant rate, which means you're going around a spiral. And in that case, if you notice, as you move further and further away, you're still traversing the 360 degrees in the same amount of time because your angular speed is increasing. And as you move away, it means you are covering longer and longer distances. The perimeter of your circle, your imaginary circle, is increasing, meaning that your velocity must increase, your speed must increase. So that also means there is some component of acceleration in that transverse direction that can lead to this increase in speed. So these four terms, all of them contribute to the total acceleration. And what else? One thing you can say, again, this is what I wanted to say last time, I couldn't. If you want to find acceleration, the magnitude, you have to consider both components, and that is r double dot minus did I press it? Minus r theta dot squared. All of these is the radial component. So radial component is squared plus r theta double dot plus 2 r dot theta dot. Again, all of these is squared because the whole thing is the transverse component. And that's how you calculate the norm if asked. And similarly, you can find the angle of the acceleration vector using these two components. So that is, I think, all I can say about the acceleration at this time. Again, derivation, feel free to look at the derivation. It is important and useful to know where these terms come from, at least mathematically. But here I want to focus on their meaning and how they contribute and why they exist in our terms. So there is one more video to wrap up this section. That would be the cylindrical frame, and I think that is the end of this part. So I'll see you in one more video, and that should be it.